All right, here we go with page 3. As you increase your margin of error, your confidence goes up. For example, if you are guessing that the average weight of a woman in the United States is between 15 pounds and 1,000 pounds, you're pretty confident that you're making a true statement. However, as you decrease your margin of error, let's say you say the average female weight is between 121 pounds and 122 pounds. That's a pretty bold statement. You've got a small margin of error. You're pretty unconfident. Your confidence goes down. So you sacrifice accuracy. Here, we're sacrificing accuracy. We are not accurate, but we sacrifice it for being confident because our confidence goes up here. So you sacrifice accuracy for confidence. All right, next thing, Ms. Sorensen calls green beans haricot verts. That is actually true. You can look it up if you want to know what they look like. They're just smaller green beans. And I'm surprised by the fact that many people don't know this term. I decided to survey 50 people to determine if it is a popular term, and I find an average of 20% of people do know what haricot verts are. It's a French word. And there's a standard deviation of 1.8%. And I'm surveying 50 people. And I've got a confidence interval of 95%, which if I go back up here, and we're talking about from 2 standard deviations here to 2 standard deviations here, you can see that this math from here to here, if we add those up, that's our 95%. So we're talking about a z-score of 2 here, right? Because we're being 2 standard deviations away from the mean. So our formula for this, as you may recall, is x bar plus or minus z times the standard deviation divided by the square root of n. All right. Let's plug in for that. We've got 20%, or just 20, plus or minus our z-score of 2 times our standard deviation of 1.8 over the square root of 50. All right, that's going to give us 20 plus, and then I get an answer right here, plugging that into my calculator. I get 0.509, but I've also got to do 20 minus 0.509. So that's going to give me a high range of 20.509 and a low range, if you will, of 19.49. Okay, so that's an interval notation, but not necessary. We do, however, have to write a final sentence at the end here. We can say that we are 95% confident that the actual average is between 19.49% and 20.509%. All right, moving forward. A sampling distribution shows every possible result of a statistic that it can take and every possible sample from a population and how often each result happens. So the sample distribution actually has the same mean as the population. And we're going to do an example of that below if you're not sure what I'm talking about. Even if the population data is not normal, which is actually the case in the example below here, then the what, the sample mean, or the sample distribution, will be normal. And again, I'm going to relate back to that at the end. All right, so here's our example. If you're not sure what's going on here, I'll come back to that in a hot second. But here's our situation. We have 4 people in the room. That's a population. We're only going to talk about 4 people. And their ages are this right here. Okay. You want to find the average of their ages, but for some reason you decide to do a sample of 2 people instead. That's kind of silly, right? You've got a population that's so small. Why wouldn't you just find the population average? But this is just an example, right? So instead of finding the population average, you're going to go and you're going to sample 2 people, and that's going to give you an average. All right, so first you go and you sample a person who's age 1 with a person who's age 2. So we've got an age 1 and age 2. That's an average of 1.5. All right, now you're going to go and sample a person age 1 with age 3. 3 plus 1 is 4. Cut 4 in half and you've got 2. So we've got an average of 2 for that sample. Then you go and you average a person with age 1 with age 4. 4 plus 1 is 5. 5 divided by 2 is a 2.5. Okay, so you've averaged those 2 individuals. Then you go and you average a sample of age 2 and age 3. 2 plus 3 is 5. Cut that in half, you get 2.5. And I hope you see a pattern here. You certainly can pause the video and find the rest. But basically, we have age average of 2.5 here, going up to an age average of 3 when we're sampling 2 people in these columns, 3.5, 4, and 4.5. We're going to go ahead and mark an X here wherever we see a value in our table. So it looks like we have 2 ages of 1.5. That was 2 samples gave us an average of 1.5. Then we have 2 2s. We have 4 here. And how many 3s do we have? We also have 4. Is that? How many 3.5s do we have? 4. How many 4s? Just 2. How about 4.5s? 2 as well. And you can kind of see that this is normally distributed. Now verify the population mean is equal to the sample mean. Well, let's find the sample mean first. So we went out and we got a ton of samples. Specifically, we got 20 samples. So I'm going to add up all 20 of these numbers. So that's going to be 1.5 plus 1.5 plus 2 plus 2 plus 2.5 plus 2.5 plus 2.5 plus 2.5. Okay, I've got 4 of those. Then I've got to have 4 3s. 4 3.5s. Okay, and I'm going to add those all up, and then I'm going to divide that answer by 20. Let me just do this real quick. I get 60 here. So 60 is what I get when I add up all of these values. So 60 divided by 20 is 3. Now let's check our answer. Does that make sense? Yeah, it sure does. It kind of looks like it's straight in the middle there, although my curve's not super great. All right, so our sample mean is 3. And so that's interesting. That's the mean of my sample distribution. Very interesting. Now let's verify that our population mean is the same. So this one's way easier. I only have numbers 1 plus 2 plus 3 plus 4 plus 5. I'm adding the ages of all 5 of those people, and that's going to give me a sum of 15. I'm going to divide that by 5 because we've got 5 people, and that gives me a population mean of 3. Okay, that's my population mean. Use that symbol mu to talk about it. Okay, so we've got 3 for the sample mean and 3 for the population mean. So they are exactly the same. I just want to quickly go back to these 2 questions. It says the sampling distribution has the same mean as the population mean. So this is a sample distribution. I'm basically finding the sample of 2 people, and I'm doing that as many times as possible. And what's the average of my results? Well, it was 3. But what was my population average? It was also 3. So our sample distribution mean is the same thing as our population mean. Now, even if the population data is not normal, right? If I were to graph this right here on a frequency chart, I've got, let's say this is 1, 2, 3, 4, 5, I'd have an X, 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 X. This actually is not normal, right? We need some sort of a curve like this to be normal. And so here, it's interesting because even though we don't have a normal distribution here, we do so when we look at our sample distribution. Okay, so that's where that is connecting. All right, thanks for watching page 3.